So in this section, we're talking about 5.2/5.3 Riemann sums and the definite integral. So in the last section, when we took the area under the curve, all the area that we did was above the x-axis. And the other thing that we did in the last section was that each width of each rectangle, delta x, remember that's what it was of equal length. So let's say we take off those restrictions of having equal width rectangles, and we took off the restriction of having the area have to be above the x-axis. Well, that's what Riemann sums basically tackles. So let's look at the definition of Riemann sums, and then we'll talk about everything. So let f of x be continuous on the interval from a to b. So if you look over at the graph, the interval from a to b, now we have some area underneath the curve and some area above the curve. Partition a to b into n subintervals of width delta x. If you look at the picture, those rectangular regions are not the same width, and that is totally legal with Riemann sums. Let x sub I be any x value in the ith interval, so x sub I is an element between x sub I minus 1 and x sub I. So that's telling you that, hey, you might have to take the left endpoint, the right endpoint, or the midpoint. Remember, x sub I minus 1 is left endpoint, x sub I is right endpoint, and x mid, or mi, is going to be the middle point. Then we define the Riemann sums to be Riemann sums equal the summation of the intervals from 1 to n of f of x sub I times delta x. So again, we're multiplying the length times the width, or the height. F of x will give me the height of each rectangular region, and then we're taking it and multiplying it by the width. Okay? So we're not doing anything new there, but notice it's not calling it area. It's calling it Riemann sums. And the reason why it's calling it Riemann sums is because when we find this, we can get negative values. So we're getting in like the net area, okay? Please note that regular partitioning is when the intervals are of equal width. So delta x is equal, like we saw in the last section. In that case, the Riemann sums is r. Riemann sums equals left n, middle n, and right n. So again, we're using the same notation as last section. So for the first example, I'm looking at the function f of x, which equals x cubed minus 1 on the interval from -2 to 2. Find the Riemann sums using the n interval of equal width. Okay. What I did was I made a chart because, first of all, I need to have the function drawn. Remember, I'm going from when n equals -2, and I'm going to +2. So that's my interval, okay? What I'm going to do is I'm going to plug -2 into the original function, -1 into the original function until I get to +2, and I'm going to plot those points, okay? So I'm going to take -2, which is my first x value. I'm going to cube it, and then I'm going to say -1. So when I do that, I get a value of -9. Okay, now I'm going to take -1, cube it, and I'm going to I'm going to subtract 1 from it, and I got -2 as a result. I'm going to plug in 0. 0 minus 1 is -1. I'm going to plug in 1. 1 cubed is 1. 1 minus 1 is 0. And then what I'm going to do for the last one is 2 cubed. 2 cubed is 8. Minus 1 is going to give me a 7. Okay? All right, so I have these values, so I kind of know what the y-axis is going to look like. So I'm going to take that up to 9. Okay? So here's +9, here's -9, and now I'm going to plot points. Okay, so -2, -9 is clear down here. Then I have -1, -2, so it's going to be here. And then we have 0, -1, which makes sense because we basically take x cubed and move it down 1 unit. 1, 0, and then 2, 7. 2, 7. Okay, so basically I get this graph, and I have my function. Now it says, for f of x equaling x cubed minus 1 on the interval from -2 to 2, find the Riemann sums using n intervals of equal width. Okay, so when they mean equal width, that means the width of the rectangle, which means the width of the x. Okay, so what I'm going to do is I'm going to use 1 unit at a time. Okay, so to do this, what I'm doing is I'm doing the width equal to those x values. Okay, so I'm going to have 1, 2, 3, 4 rectangular regions. Okay, so if I draw my rectangles in, remember I'm using midpoint. So I'm going to do -2 to -1. That midpoint would be -1.5. Okay, so that value is here. I hit the curve. Okay, so that's my first rectangular region. I'm going to draw that in. Okay, the next one is going to be from -1 to 0, which is -0.5. And guys, the reason why I'm using this midpoints is because they told me to do that. So again, hitting the curve, and then we're going to do this. So these are my first two, and notice they're below the x-axis. Okay, the next one, in between 0 and 1 is 0.5, so I find that point, go down to the curve, and I draw that in. Okay, so when I draw that one, it's still under the curve. So see how that's under the curve? And then the last one I find is halfway between 1 and 2, so that is 1.5. Again, find that midpoint, come up to the curve, then draw the rectangle region in. Okay, so I'm going to highlight what this looks like. Here's the first one, second one, third one, and fourth one. Okay, all right. So now that I have those values, I just need to know what the width is of each rectangular region, and I have to multiply that by the height. So remember, Riemann sums looks very, very familiar. So I equals 1 to 4, because I have 4 rectangular regions. And then we're going to do the function. And this is x mid, because remember, using the middle point. And then we're going to take that times delta x. Okay, so delta x is the width. And remember, the width of each rectangular regions is 1 unit. So delta x equals 1. Okay, so this looks like this. Delta x, which is 1, times my function at -1.5 plus my function at -0.5 plus my function at 0.5 plus my function at 1.5. Okay, so what we're going to do is I'm going to throw that into the calculator. We're going to calculate that. So I'm going to take parentheses -1.5, and I'm going to cube it, and then I'm going to subtract 1. So I'm plugging it back in the original function. And when I do that, I get -4.375 plus -0.5. We're going to cube that and then subtract 1. And I got -1.125 plus, now we're taking 0.5 and cubing that, -1. I get 0.875, and it's negative. And finally, the last value, 1.5 cubed -1. I got 2.375. Okay, so 2.375 here. All right, so I'm going to multiply that by 1. So I'm going to add those all up. So -4.375 plus -1.125 plus -0.875 plus 2.375. And I'm going to double check to make sure I entered everything in correctly. That looks good. Hit enter. I get -4. So 1 times -4 is -4. You'll notice that you got a negative number. And remember, that is not the total area. That is the net area. And again, Riemann sums don't give us the total area. It gives us the net area. Okay? So you can get negative values with Riemann sums, even though it's kind of weird. And the reason why is because in that example, we had regions underneath the x-axis. And we had more regions that were underneath than above, and that's why that thing came out to be negative. All right, so let's look at the definite integral. So let f of x be continuous on the intervals from a to b, and they're partitioned as above. When they say above, they mean to the right here. Okay, so we're looking at this graph. Okay, so if you look at the graph, you're seeing that I have areas that are above the x-axis and areas that are below the x-axis. So when we use a definite integral to find the area under the curve or area above the curve, let's see what happens. Okay, so the definite integral of f of x on the interval from a to b is defined to be the integration from a to b of f of x dx is equivalent to the limit as n approaches infinity of the intervals from 1 to n, the function times x sub I times delta x. So what they're saying is I have infinitely many rectangular regions underneath or above the curve. Okay, when I have those in like those teeny tiny rectangles, then that means I get a more precise value of the area. Okay, so please note that the definite integral is a number. Geometrically, the definite integral represents the net area, so we still might get negative values. Okay, so I'm just letting you know, watch out. Okay, so I'm going to stop the video here and I'm going to do a part 2, but I just wanted to introduce to you what the definite integral is doing.